In previous videos, we've looked at how to do long division with polynomials, and we've looked at a shortcut called synthetic division. In this video, I'm going to introduce a topic called Remainder Theorem. Where this is going is ultimately going to allow us to factor larger polynomials than we've been able to in the past. So let's look back at long division. If we have a statement like 46 divided by 7, or a question like 46 divided by 7, and we do it by long division, we get something that looks like this. 46 divided by 7 is 6. Multiply back to do the long division, we get 42, subtracting is 4. So 46 divided by 7 is equal to 6, remainder 4. We could write that alternatively as 46 is equal to 7 times 6, the divisor times the quotient, plus 4, the remainder. Similarly, this is our example that we looked at previously for polynomial long division. We could rewrite this as the dividend, that polynomial we started with, is equal to the divisor times the quotient plus the remainder. Here's that statement again. The dividend is equal to the divisor times the quotient plus the remainder. Now, I'm going to name this f of x, this function that we've been dealing with all along. And now I'm going to ask, well, what's f of 3? Now, I haven't picked 3 by chance. I'm picking the number 3 as the number that makes the divisor equal to 0. In fact, we encountered that number before when we were looking at synthetic division. It was the number we wrote on the left. I'm going to call this number, the number that makes the divisor equal to 0, a. In other words, the divisor is of the form x minus a. The divisor is x minus 3. I'm asking what's f of 3? Well, as you know, to evaluate a function, you substitute that value in everywhere you have x. So f of 3, we substitute in 3 everywhere, and we end up with 14, which is the remainder that we got when we divided by x minus 3. Is that a coincidence? No, it's not. Take a look at the statement above. This is an equation, so the left side and the right side have to remain equal no matter what we substitute in for x. If I substituted in 3 to evaluate the function that x is equal to 3, I subbed it in all of these places. Now notice here, if I substitute in 3, I get 3 minus 3, and this becomes 0. That means it doesn't matter what happens over here, this whole part is going to be equal to 0. And then I've got my plus 14 at the end. So the right-hand side is going to become 0 plus 14 is 14, which means the left-hand side must also be equal to 14. What we found is when we substitute in a value, in other words, when we evaluate the function at the number that makes the divisor 0, in this case at 3, the answer we get is the remainder. Another way of stating that is that when a polynomial f of x is divided by x minus a being any number, the remainder equals f of a, and that's what we call the remainder theorem. Again, when a polynomial f of x is divided by x minus a, the remainder equals f of a. Let's look back one slide. So here, when this polynomial f of x was divided by x minus a, in this case x minus 3, the remainder was equal to f of 3. Again, when f of x was divided by x minus 3, the remainder was equal to f of 3. And we saw the reasoning here, because 3 made this become 0. This all disappeared, and all that was left on this side was the 14. So that's the remainder theorem. And that gives us a shortcut for figuring out remainders without actually having to do the long division. So here I've introduced a new f of x. Let f of x be that. Find the remainder when f of x is divided by x plus 2. So you can think of this as being x minus negative 2. So it fulfills the x minus a criteria or setup. That means that a is equal to negative 2. So we sub negative 2 into the function, and we get negative 35. That means the remainder when this function is divided by x plus 2 is negative 35. And that's the remainder theorem.